a lot for the invitation. It's a pleasure to speak here. So given the name of the seminar series, I probably don't need to explain why we should be doing studying thermal physics, thermodynamics. There are many applications across condensed matter physics, energy physics, and especially in recent years in understanding strongly correlated systems at finite temperature. And the tools we have there are a little more limited than at weak coupling. There's kind of, I would say, two classes of tools. One is effective field theory, where the mindset is to, even though the original degrees of freedom are strongly coupled, try to find degrees of freedom that have effective weak coupling dynamics, and then you can acquire control on the system in that way. And more kind of non-perturbative, let's say UVIR constraints, things like sum rules, analyticity, anomalies, bootstrap, which try with as few assumptions as possible to constrain the emergence. There's been a lot of recent progress on applying this at finite temperature. And I think kind of looking ahead, where I see really the most promise is in combining these two things and really understanding their interplay. So, given that I know there are many bootstrap experts here, I think it's interesting to talk together. So my past work is mostly on effective field theory, and I'll mostly be talking about that today. But I think the interplay is really interesting for the future. And of course, other non-perturbative methods include numerics and experiments, which are not perturbative. I will talk a little bit about numerics and how you can use that to test some of the effective field theories that I'll be discussing. And I apologize that my references aren't completely, I didn't quite have time to put all references on the slides, but I have some recent TASI lecture notes that I invite you to look at if you want a more complete list of references. So the name of the game for today will be to try to make predictions for observables, for dynamical observables in a thermal context. So, let's say correlation functions of local operators in a thermal state. Let's say we put our system in a finite volume, just so that we have a kind of nice bounded discrete spectrum, bounded Hamiltonian, a density matrix. And then the name of the game is to try to find predictions for observables of this form. So this isn't all the possible observables you might care about. This won't include, I won't include in this talk out of time ordered correlators or things like entanglement, extended operators, and I'm very interested in extending the techniques I'll talk about to observables like this. But just to keep this talk a little bit contained, we'll focus on these slightly more conventional observables. And in fact, as a first kind of warm-up, we'll focus on a simpler problem of static observables. So of observables where you integrate these operators over time, okay? Which corresponds to asking about the response of your system in thermal equilibrium to time-independent probes. Okay, so equilibrium thermodynamics. We'll start with that. Right, so one point that probably most of you know, we can, instead of working in real time, we can work in imaginary time by considering our quantum field theory on the cylinder. Since I'm going to integrate over time anyways here, this won't be I won't lose much by doing this, but we'll come back on this point later. And so to generate correlators that are time independent, all we need to do is to couple the operators we care about to time independent, to static sources. Okay, you could do this with any operator. I'll focus for simplicity on the stress tensor, the preferred operator, which exists in any local quantum field theory. So you would couple your system to a metric, let's say on the cylinder, and I'll make that metric only depend on space. Okay, and here I wrote it in a Kaluza-Klein kind of reduced form where I expressed it in terms of the lower dimensional spatial metric and a kind of gauge field and dilettante. So then the object that we'd like to understand that will generate all these static correlation functions of stress tensor is this object here, the generating functional of this method. So, you might worry that this will be a complete mess, but there is a very important simplification in this thermal context, which is the existence of a finite correlation length or finite thermal mass. Okay? Very generically, we expect thermal, quantum many-body systems at finite temperature to have a finite correlation length, which means that observables decay, local correlation functions decay exponentially eventually at very long distances. And And this finite correlation length will imply that you could imagine integrating everything out, and you'll get a local generating function. Okay, local on this scale, meaning that it will satisfy a nice gradient expansion, which will allow for it to organize this generating functional with higher derivative terms suppressed by this scale. Okay, and this is what this generating function would look like. It has to be, diff invariant for the reduced metric, gauge invariant for A, and then it can depend on this dilaton-like field. So at zeroth order ingredients, you'll have a kind of cosmological constant type term, which can be a function of the sigma, and then there will be higher derivative terms and so on. Okay, so this thing involves entire Wilson coefficients, functions of this e to the sigma, which as you might know, so is more of a feature and not a bug. It might seem like it doesn't have much predictive power, but actually it contains the whole equation of state of the quantum field theory, right? This thing, I wrote it suggestively, it's the pressure as a function of, eventually this will be temperature. So it really has a lot of information. And typically you might be interested in expanding this around some temperature and studying fluctuations. So there's a lot of non-trivial statements that come from this thermal effective action. For example, it's going to relate the leading, the partition function on the flat thermal cylinder to expectation values of the stress tensor and to higher point functions of the stress tensor, and so on. And there's been some recent interest in applying this to CFTs, where these scale invariance further constrains these Wilsonian functions to be just numbers, so that the action is even simpler. So I don't have all references here, but there's been some progress in expressing heavy OP coefficients using this thermal effective action when the heavy operators are not too close in dimension. So this is kind of the tools we have for equilibrium physics, and with this quick review done, I'm going to move on to dynamics, which will be the main focus of the talk. So time and space behave very differently in a thermal context, right? So they're obviously allowed to, because finite temperature breaks Lorentz invariance. But I think it's important to emphasize how differently they are, okay? So while we expect correlation functions in space to decay exponentially, the generic expectation in time is that actually they decay extremely slowly because of conservation laws, right? So if you have, if you imagine a 2-point function of a conserved charge, that doesn't decay at all. And so similarly, you would expect a very long wavelength modulation of your charge 2-point function, or energy, stress tensor 2-point function, to decay extremely slowly. And if you Fourier transform the statement, it leads to instead polynomial generically decay in time. Okay, so it's a very different type of behavior than the spatial behavior. You could say, very loosely speaking, that there's generically some kind of long-range order in time in thermal states. And what this means from an effective field theory point of view is that, for this equilibrium situation, we could integrate everything out, and our effective description just involved background fields, right? Whereas here, there's really actually stuff left, right? There's long-range correlation. So there's going to be long-lived fields that we want to keep in the description. So the effective field theory for real-time dynamics will contain actual dynamical fields that are being path integrated over, that we'll want to keep in the description. Okay, so how do we capture this this effective field theory? So we're going to have to work in real time, and so you might wonder, why are we working in real time? I prefer to work in imaginary time. I like the thermal cylinder, and we can analytically continue anyways. But analytic continuation is possible when you have an analytic expression. But in most situations of interest, we'll only have access to maybe a perturbative expansion. Let's say the OP limits, small imaginary times, and you can't analytically continue that. And so the strategy here will be to directly perform any approximations we think are relevant in a real time kind of formalism, so that we directly have access to the, let's say, universal late time dynamics that we're interested in. I should also say that, the universality arises at late times, which is encoded in a very complicated way on the thermal cylinder, where tau goes from 0 to beta. Right? So it's highly non-trivial how you would see these things in imaginary. So again, we'd like to compute observables of this form. I have a density matrix, a string of operators that I care about. And to do this, we have to time evolve not the ground states like in, usual in particle physics, but a mixed state, a density matrix. And so this will, a density matrix naturally has two legs. And we'll do this by, again, coupling to sources so that we can generate correlation functions that we want. And I'm going to couple to different sources on both legs of the density matrix. Okay, if it were the same source, that would just give me one, right? Because they would cancel. But allowing for different sources gives me a non-trivial object, which I can then, differentiate with respect to J to get correlation functions that I like. And in terms of your in path integral language, in terms of your microscopic QFT action, this is what this object would look like. There's a forward time evolution, backward time evolution, and there's crucial boundary conditions which tell you about what's happening on both ends, right? So at plus infinity, the fields are identified. At time minus infinity, they're correlated in some way, because the boundary condition is weighted by the density matrix. And so these fields are highly correlated. The two legs know about each other. So this is the setup, okay, the Schwinger-Keldysh contour setup for real-time dynamics. You could do microscopic, say, perturbative quantum field theory in this setup, but we'll try to do effective field theory. And because we're going to do effective field theory, it's going to be crucial to know some general properties that this partition function has, which would be automatic if you were doing microscopics. But in the effective field theory, these properties we're really going to have to impose them by hand to help us guide us in constructing these effective field theories. So the first very simple property that I already mentioned is that if you set both sources to be equal, trace by trace cyclicity, you'll just get trace of rho, which is 1. You could say the kind of whole contour has collapsed because you time evolved and time evolved back with exactly the same operator. There's some unitarity condition, like the conjugate of Z just exchanges the two U's, so it exchanges the two sources. And finally, there's an important property that comes from the fact that the density matrix isn't some arbitrary density matrix. It's the thermal density matrix that we're interested in, which basically looks like time evolution in imaginary time. And so you can use this to get this KMS condition by, basically commuting the density matrix across one of the unitaries, and that gives you a relation on this partition function, that it's related to itself at a shifted time. Okay, this is the analog of periodicity in imaginary time, but in this real-time context. There's a slightly more refined version of the first condition that you can figure out, which will be useful for us, which is that you don't need to collapse everything. So if you have a string of operators in your correlation function, and then you look at the very last operator, well, the very last operator can be placed either on contour 1 or contour 2 by trace cyclicity, right? You could either put it here or here. It's the latest operator. That will give you the same correlation function. Okay, so this kind of latest time condition is will be useful in constraining our effective field theory. Okay, so these are all kind of very general conditions. And I should say, please stop me if you have questions. Not the second part. Yeah, so let's say we look at this guy, and there's an operator here. The point is that the difference between putting this operator here versus here means commuting it across that operator, right? So imagine this trace with a string of operators. There's one that's really at the latest time, then there's one that's at the second latest. If I want to put it on the other leg, I need to commute it across this operator, then use trace cyclicity. And they won't commute. Yeah, so that. Exactly. The important thing is the order along the contour. As long as you hit nothing along the way, you're good. Thanks for the question. Okay, so let's see. So now let's try to build an effective field theory that will respect these things. So the hardest step in effective field theory is identifying the right degree of freedom. Once you have a good idea for what that should be, usually you're just guided by symmetries and it kind of becomes a simple algorithm. But the key step is finding the right degree of freedom. And the context where it's most obvious is in when you have symmetry breaking, right? When you have Goldstone's theorem that tells you you have specific light modes. That's how you would build the high-on Lagrangian. And as we'll see, there's a symmetry breaking kind of paradigm behind hydrodynamics. But to understand this, we'll have to think a little bit more about symmetries in this context of mixed states. And as we'll see, they're a little bit richer. In particular, there's a natural notion. So if you have a quantum field theory with a specific symmetry, here I'll illustrate this just with a U1. Let's say I have a single U1 in my symmetry, global symmetry of my quantum field theory. There's a natural notion of a doubled action of this symmetry on both legs, okay, or on your density matrix. Now, this sounds a little bit useless. Why am I telling you to just double every symmetry in your quantum field theory? I'll give you one context where this would be a reasonable thing to do, which is in fact the context where it was first introduced. And it's the context of open dynamics, where you don't have unitary evolution. So we're interested in a density matrix evolving with the Whewell equation, right? But this evolution, because the Hamiltonian commutes with Q, is indeed invariant under action both on the left and the right of the density matrix. But in the context of open dynamics, people consider a generalization of this equation called the Lindblad equation, where you act in a non-unitary way. Okay, and so here, if you imagine that this Lindblad operator has charge, is charged under your U1, you're no longer satisfying this both symmetries independently. You're only satisfying the diagonal or the weak symmetry. And this can model, a system that's coupled to the bath and it's exchanging charge with the bath. So in this context, it makes sense to slightly generalize this notion of symmetry, because we could have either strong or weak symmetry. Strong where you have both left and right, and weak where you just have the diagonal. And interestingly, in this context of open systems, weak symmetry also gives you some, you might think you lose everything, but it also gives you some non-trivial constraints on your dynamics. But why should we care about this in closed systems? So we care about, the universe is closed, or we care about a quantum field theory, a closed quantum field theory. Well, it turns out that, and this is a kind of proposal from the past, let's say 2 years, that one can think of hydrodynamics as, or that generically one should think of closed systems as spontaneously breaking every symmetry down to weak. Okay. And maybe a loose intuition for that, I guess, I think okay, maybe I removed this slide. The loose intuition for that is that while a pure state, you can act on the left and the right, and that will just give you a phase. A thermal state, if you act on the left and the right with different charges, that'll give you a different mixed state. That's a kind of, let's say, intuition for that. You can also build actual order parameters that would be charged under this off-diagonal symmetry, in a kind of regular spontaneous symmetry breaking, let's say, order parameters. So we're going to take this as the kind of assumption which guides us into what are the right degrees of freedom. So the paradigm here will be that we'll view hydrodynamics as Goldstone modes for strong to weak spontaneous symmetry breaking. And I should say, so I really like this way of thinking of hydrodynamics. It's obviously very recent, and hydrodynamics is an extremely old field. What I like about it is that it puts hydrodynamics on the same paradigm as, let's say, the chiral boson Lagrangian. It really becomes a simple algorithm. It also puts it on the same kind of, unifies it with the dynamics of open systems, and there's a nice review on this. But I should say, this really kind of is benefiting from a lot of previous work on trying to understand effective field theories on Schwinger-Keldysh by various groups, in particular Hong Yu and Lopanagagan and Ramani. And so this is kind of, I would say, but if I had to teach hydrodynamics, I think I would do it in this way now. I think it's a kind of much simpler way to think about hydrodynamics. So let's see how we would do this now. So let's build an effective field theory for this type of symmetry breaking. So as a warm-up, let's first pretend we don't have strong to weak, but strong to nothing. So let's pretend we have, you know, G1, G2 symmetry on both legs. Let's say they're both U1s for simplicity, and that it's just completely spontaneously broken. Everything is spontaneously broken. So you would expect to have two goldstones that both shift under the simple U1 symmetry, and then we'll write down an effective field theory for this. It's convenient to slightly change basis and do what's called a Keldysh rotation, where you consider, instead of phi1 and phi2 on both legs, you consider the difference field and the average field, because they have some nice properties as we'll see. And then you just write down the most general action you can. Here I just wrote up to the quadratic order in the goldstones and leading order derivatives. I need derivatives, either time or space, because of the shift symmetry. There's no, Lorentz invariance that I have to impose, so these are all independent coefficients. One thing I did here is that, notice I have some phi a squared terms. I have phi a, phi r that mix the goldstones, but I have no phi r squared term. Actually, this is necessary to guarantee, once you invert, this diagonal, this Gaussian action to get the propagators, to guarantee that there's no phi a propagator, because a phi a propagator has to vanish, since we just discussed, right, this latest time condition that the latest operator, you could either put it at 1 or 2, there's no difference. So if it's an A field, 1 minus 2, that should vanish. Okay, in particular, the 2-point function of phi a has to vanish exactly for all times. So you see, it's a little bit funny from the perspective of effective field theory. We have all these conditions which are not quite symmetries. They're kind of properties of the partition function that we need to impose, in a sense, perturbatively by hand. But that's how it is. So that's one thing. Another condition is the KMS symmetry, which will fix certain coefficients in the effective action. So the KMS symmetry, remember, relates your partition function to a time-shifted partition function. You can realize that directly on the fields and expand. So we're interested in, this is an effective field theory that is valid at late time, so we can expand and we can Taylor expand this plus I beta, and it's going to act in the A and R basis by mixing the two fields in some way. So that'll give you some constraints. We'll see one such constraint in a little bit. Okay, but this is not exactly the effective field theory we want. We want an effective field theory where instead, so by the way, this effective field theory that we have here does describe something. It is completely physical, but it would describe a symmetry broken phase. So it would describe, let's say, a superfluid. If you want a lattice model, that would be the XY model in the ordered phase. At finite temperature, it's going to have, dissipation, and it'll have, but it will have a sound mode, superfluid sound mode that has this dispersion relation. Now we'd like to be in the normal phase without actual symmetry breaking, only this new type of mixed state symmetry breaking, where our doubled symmetry is broken down to the diagonal. Okay, so still just U1 for simplicity. So now the effective field theory should just contain one goldstone. Okay, this Keldysh kind of off-diagonal goldstone, right? That's the symmetry that's being spontaneously broken. But we still need to realize these other conditions, realize KMS symmetry, for example. And KMS symmetry, before it was mixing A and R fields. And to realize them, you're basically forced to have a Keldysh friend, right? It's this kind of doubling of fields on a Schwinger-Keldysh contour. It's hard to realize KMS symmetry without two fields. And so the simplest way to realize KMS symmetry in this context where you have one goldstone is to still give it a friend, but this friend is not non-linearly realizing a symmetry, right? It's linear. You would call it a matter field, let's say, in EFT language. But it's going to have the same transformation properties basically as phi r dot would have had. Okay, so it does not shift under symmetries, but it is part of this KMS multiplet. Okay, so that's kind of the simplest way to make sure we can satisfy all these constraints. And then now that we've identified the fields, we can try to write down their action. So we have to satisfy this shift symmetry under phi. Interestingly, so mu r doesn't have any shift symmetry, and so I can just write their mu terms. And you see that the scaling of time and space is very different, right? So there's I'm assuming let's say isotropy, where we have rotation invariance, and you see that I have one time derivative and two spatial derivatives. Okay, so this is eventually going to lead to diffusion. there's some other terms that one can write down, and it turns out that this term that involves two phi A fields has the same coefficient as this other term due to the KMS symmetry. So this is kind of a consequence of KMS symmetry. It's what would have been called in the old days fluctuation dissipation relations. This is relating these two coefficients. It's a leading order KMS symmetry. So this is our kind of leading order action. You can identify, the density related to the U1 by. So the cleanest way to do that would be to couple the background sources and differentiate with respect to these sources. I won't do that here, but you can do something that's basically equivalent, which is to find the field that's conjugate to phi A. So take the derivative of the action with respect to phi A dot, and you'll find that the density, the actual U1 density of your system, is related, to leading order simply to this mu field. Okay, in a relation that you can see, so there's some Wilsonian coefficients. I gave them suggestive names. Mu you can kind of think of as a dynamic chemical potential, and chi is a little bit like this. Maybe you could change variables to the density. In fact, I'll do that because maybe it's a little bit more intuitive what density means. So this is the action that we've obtained. We have a Lagrangian for 2 degrees of freedom, one kind of Goldstone, and a density. This Goldstone is related to what in older approaches to hydrodynamics would have been called a noise field. It's kind of similar to that. And our action, as usual in effective field theory, will have many corrections with Wilsonian coefficients. In fact, it will have Wilsonian functions, very similar to the thermal effective action. Things can depend on density. I've given these coefficients suggestive names. This will be the diffusion constant. This will be the conductivity. But they can have a nonlinear structure to them. And there's obviously many higher derivative terms, many terms with more noise fields, and so on. So any questions about how we get to this effective field theory? We'll soon start using it.
Maybe I have a question. So
Yep.
I see how how this works, but is there some statement that this is the only way to make KMS symmetry work, that you have this density field?
Yeah, no, that's a good question. So there's one step that's maybe not super satisfactory, which is my statement that you need, specifically this matter field. I think you could probably show something like that. I think you could probably, so, obviously you could have more matter fields, but then you could probably integrate them out. And the one that mixes with your Goldstone is the one that is going to feel, kind of be gapless because it's mixing. And so there's kind of one linear combination of matter fields that you can't get rid of. Maybe you could ask, can I build a putative effective field theory without that matter field at all? I suspect you could, you could. I wonder if you could try to show that's impossible. Or maybe that you would just land on exactly, maybe you would just land essentially on, on essentially the same description. Yeah, let's see. Yeah, I think you would basically land on the same thing. So there's that would tie more to maybe to tie to earlier approaches to hydrodynamics. You could try to integrate out mu r and see what you get, right? I think it would be a little bit harder to impose symmetries and so on, but you could. But I'm guessing it would be equivalent to doing that. But yeah, it would be nice to make this maybe a little bit more precise and saying that there's no other way, right? Because these, KMS and all these things, these collapse rules are not really symmetries. It's a little hard to formulate it as, there's only one way to realize these symmetries, or classify ways to realize these symmetries. But yeah, it would be nice to have something like that. It's true that here I'm mostly just telling you this is one way to do it. Okay, very good. So now with this action, you can compute things. The simplest thing you can look at is the propagator of these fields. There's some, I guess I won't go too much into details. There's some map into the 2-point functions of phi A's and N's and how they translate to more let's say familiar Green's functions like the retired Green's function, but that's all fairly simple, and you would find a diffusive 2-point function for charge. But you can obviously go beyond that, and that's the point of effective field theory, is being systematic. And in particular, you can see that the leading nonlinearities in this way have been in this action will come from expanding the diffusivity and the connectivity as a function of density. Okay, these will lead to nonlinearities, nonlinear vertices, which will have a number of consequences. They will give you nonlinear response through, let's say, cubic vertices in your effective field theory. And these vertices will also feed back into linear response, into the 2-point function we talked about earlier, as corrections to transport. Okay. And the non-trivial content of the effective field theory is that it's really connecting all these things, right? It tells you, and this you could directly go to experiments, right? If you measure a diffusion constant that depends on temperature or density, it tells you that necessarily there's nonlinear response, and also tells you necessarily there's going to be loop corrections to transport. So let's look at these. Let's look at some of these corrections. So you can compute this loop correction. It will give you, here I've packaged it just kind of by choice. I didn't really have to do this, but I've packaged it as a correction to diffusion constant. And it has this interesting analytic structure where it has basically, so the leading order diffusion correlator had a simple diffusive pole, whereas this loop correction has a branch cut with a branch point halfway to the diffusive pole. So it's actually closer to the origin. It's pretty similar to the multi-particle continuum you have in quantum field theory, when you have a threshold onset of 2-particle or 3-particle production. Except here it's closer to the origin, basically just because of the kinematics. So there's a simple way to figure this out by the usual kind of cutting type arguments. So it's a kind of interesting feature of diffusive kinematics that this is happening. And as you might expect, if you keep on doing this, if you have higher and higher loop corrections, they will lead to branch points closer and closer to the origin. So in a sense, you might worry that this makes things more and more important at low energies in the IR, and that the whole expansion is uncontrolled. Now, of course, these non-latticity are more and more suppressed by K or omega, right? So if you actually plotted these functions, the mistake you're making by ignoring higher loops is still very small, but it's true that you are kind of getting more and more non-latticity closer to the origin, and there is an important consequence of this, which is something I probably won't have time to talk about, but some observables are very sensitive to these effects, and there's some sort of dangerous irrelevance in the context of hydrodynamics where you're at very late times, because you have these non-laticities very close to the origin, you're very sensitive to these effects. But,
does this simply means that this Lagrangian makes sense only with an ER cutoff, or it's deeper than this?
No. So it doesn't need an IR cutoff. So that would be very troubling, right? The Lagrangian doesn't need an IR cutoff, and for many observables, you really have a controlled expression for them, where you could, as usual in effective field theory, and we'll go to some examples. Let's see, is it already in the next? We'll very quickly go to some examples where you have for local correlation functions, we'll have a very nice perturbative expansion. Okay, but there's a set of observables which maybe I can come to in the end, depending on if we have time, where somehow these loop effects eventually dominate, and the effective field theory kind of predicts its own breakdown even at very late times, which is pretty unusual. But I would say most observables were good, and it really is a kind of well-behaved effective field theory. Or said differently, interactions are irrelevant, and so there's smaller and smaller corrections at late times for most observables. So good. So let's actually try to test some of these things in numerics. And so this is work done with many fantastic colleagues, both analytic work and numerical work. Maybe the most recent with Silvia Papalardi, where we kind of went and really tried to test beyond simple diffusion, test the more these more subtle kind of corrections and nonlinear response in various systems, both classical and quantum, including even, flow case systems where energy is not conserved, but you have, let's say, you impose spin conservation. And in the numerics, it's kind of nicest to work in real space and time. So, we can Fourier transform all of our expressions. This is what diffusion looks like in space and time. It looks like a Gaussian that spreads in time. In one dimension, it would look like this. And you can write it here. I've written it in a kind of nice scaling form where there's some overall decay with time, 1/√t in one dimension, 1 + 1t. And then there's some scaling function of this scaling variable. Okay, this is the natural scaling variable in the context of diffusion. Now, effective field theory doesn't just tell you this; it gives you a whole, systematic framework to understand corrections to this behavior. And there's going to be a lot of corrections, but we know how to organize them. There's basically two axes in these corrections. One axis is higher derivative corrections to hydrodynamics. Okay, hydrodynamics is a derivative expansion. And so these, and these higher derivative terms in the context of diffusion, you always have two spatial derivatives just by, let's say, isotropy, or one time derivative. So they're always suppressed by 1/t, integer powers of 1/t. But hydrodynamics is also an expansion in fluctuations of the noise field, of the density. And so these will also lead to corrections, to loop corrections like the one that we just computed. And so how big these corrections are, or how suppressed these corrections are, depends on dimensionality. Here I didn't put the general kind of power, but in one dimension it would be 1/√t suppressed. Okay, so in fact, in one dimension, the leading correction comes from these loop effects. And of course, you could have combinations of, one loop, one higher derivative, and so on. And what's interesting is that these corrections, so they come, there are some unknown Wilsonian coefficients in the action, but up to a handful of unknown coefficients, these scaling functions are completely universal. They're going to be the same for any diffusive system. And the effective field theory can predict these scaling functions. So the leading one is the one that you are familiar with, just the Gaussian of how diffusion looks. Okay, this is how diffusion looks in any diffusive system. But the loop correction we just computed, you can Fourier transform it, and you'll get some expression, some horrible expression, or maybe not too bad, which looks like this. And so up to the prefactor, which is not universal, although in this case, it depends on simple things that you could measure: susceptibility, diffusivity, and the derivative of diffusivity with respect to density, which caused this vertex. It's a universal, it's an entirely universal function, and it would be the same for any diffusive system. This is a very testable prediction of the effective field theory. And you could go on and measure, predict these higher ones as well. So the first kind of test of this that we did is in an extremely simple system where the numerics was, as straightforward as possible. So this is in a classical lattice gas where I have particles hopping left and right. Number of particles is conserved, and the evolution is stochastic. So it's not, actually doesn't have energy conservation, but there's a conservation model. And it's a class of model where, due to, classical magic that I won't go into, the diffusion constant is actually known. It can be obtained analytically. And so, which is kind of nice because, this whole expression will have zero fitting parameters, right? There's this leading bit, which is completely fixed, and the subleading bit also only depends on diffusivity, and it's completely fixed. Okay, and so here you can actually test this. This is the density 2-point function as a function of the scaling variable y, x/√t. And you see that it indeed approaches this Gaussian form at late times. Okay, blue is early times, yellow is later times. But there's still a slight, the data doesn't completely collapse. This, by the way, is rescaled data, √t times the 2-point function, so that I remove this. So the data doesn't completely collapse, and it shouldn't completely collapse because of these power law corrections to diffusion. And in this context, you can actually subtract the leading bit because we know it analytically, and study what's left. This is a plot of what's left. The dashed line is the theory prediction. And so you see that there's very good agreement between the numerics and this scaling function. Okay, so this is the one loop scaling function of diffusion, which should, is universal, should be the same in any diffusive systems. Okay, let me maybe skip this. So one interesting aspect of this correction, which I think is pretty interesting from the numerical perspective, is that it's actually positive if you evaluate it at x equals 0. So if you look at the 2-point function at x equals 0, it's positive. And so this tells you that diffusion is always approached by above. Okay, and it's approached by above, and the subleading correction is not very small, right? In one dimension, it's not very small. And so this is a kind of important word of caution in one-dimensional numerics, where there's a lot of very interesting activity on trying to find systems that aren't described by regular hydrodynamics. Okay, that would be very interesting to find, some local, let's say, spin chain or whatever that has anomalous hydrodynamics that we don't, that is non-diffusive. But it's very tempting, if your numerics is not extremely good in extremely late times, and you try to identify an exponent at these intermediate times, you'll always think you have super diffusion. You always think you have a larger exponent. If you try to fit this to some exponents, you might be tempted to conclude it's maybe KPZ-like, just because the correction always makes vanilla diffusion look super diffusive at intermediate times. So this is, I think, an important word of caution for numerics. You can also compute nonlinear response, as I mentioned. This is here I'm showing data in a quantum system where we first measured linear response 2-point functions to obtain the diffusion constant, and then our hands were tied. We looked at nonlinear response. All the coefficients were fixed, and compared the data. So obviously there are many, there's a lot of data in nonlinear response here. I chose a specific configuration of operators, and you see that there's a pretty decent agreement with the theory prediction and the numerics as it goes to later in the times. And this is also in Hamiltonian systems, where we did a lot of these checks as well. So yeah, so that's basically what I wanted to say about these numerical checks and how we can really do precision tests of these effective field theories. And I think these effective field theories are now really ripe and at a level where we understand them really quantitatively. Yeah, I think there's kind of exciting that builds confidence in these effective field theories and to extend them to maybe more complicated observers. So in the last part of this talk, I wanted to take a step back and ask the question of when so these effective field theory of hydrodynamics is not a microscopic description. It emerges, but how early can it emerge? How quickly can the microscopics allow for hydrodynamics to emerge? And this connects to this question of Planckian thermalization. So how fast a many-body system can thermalize. We know that at weak coupling, there's certainly no upper bound in the time scale it takes for a system to thermalize. If you're free, you won't thermalize. If you're very weakly coupled, it'll take a very long time to equilibrate, following let's say Fermi's golden rule. But the kind of collection of strongly coupled examples from holography, SYK, and so on led to the realization that you probably can't keep on making systems thermalize faster and faster, and there's potentially a limit to how fast the system can thermalize. So this is this Planckian conjecture of the local equilibration time, and you would expect it to be approximately saturated and strongly coupled CFTs, let's say, in more than 2 dimensions, or QFTs. But this conjecture has remained a conjecture for many reasons. One of them is that we need a sharp definition of this equilibration time. One definition that you might be tempted to have is to look at the decay, the exponential decay of non-hydrodynamic operators in a thermal state, and to look for the slowest one and just say, okay, that's going to be my equilibration time. And in the context of holography, this would be like looking at non-hydrodynamic quasi-normal modes, look for the slowest non-hydrodynamic one, and claiming that one is bounded. So this obviously is a reasonable thing to do in a large class of systems, but there are many systems where you don't have exponential decay at all, including simple spin chains and QFTs, just because of hydrodynamics. Let's say this in this transverse plus longitudinal field Ising model, you can look at any local 2-point function and it's going to decay polynomially. Any spin will decay polynomially because it overlaps with energy density, which is conserved. Even if you try to remove this overlap by hand, you'll overlap with energy density squared, and so you'll have a kind of you'll see the two diffusion continuum, and you'll decay a little bit faster, but still polynomial. So certainly there's situations where no exponential decay occurs in it for any local operator, and we'd like to have a definition that applies generally to that as well. And so one definition that I think is quite reasonable is as basically to define the equilibration as the emergence of hydrodynamics. Since we know hydrodynamics emerges, you could at least first loosely define the equilibration time as the time scale at which, let's say, your numerics starts looking like the expected power law decay. But you can actually make this statement a little bit more precise by looking at these corrections to hydrodynamics, these intermediate time corrections that we talked about. So these corrections, are basically preventing hydrodynamics from emerging, right? They're telling you what's really interesting about them is that it's that effective field theory telling you that it inevitably, takes time for it to emerge, because if you don't wait long enough, you have these corrections which become uncontrolled. So they will naturally kind of give you a bound on how early hydrodynamics can emerge. Okay. Now, most of these corrections come with unknown coefficients. They're just independent Wilsonian coefficients, hydroderivative coefficients. But one thing that's interesting about the loop corrections, and there you really have predictive power from the effective field theory, is that we saw that they were completely fixed by simple parameters that you could already measure, like the diffusion constant and its derivatives with respect to density. And so this gives you, if you have, let's say, a system, the diffusion constant, its density or temperature dependence, it tells you that inevitably there's going to be these intermediate time corrections, and it gives you a time scale that you need to wait for these to no longer be order 1. Okay, so that hydrodynamics basically knows about its own breakdown, right? As usual in effective field theory, it has a strong coupling scale, and it tells you it's not consistent for this set of transport parameters to emerge too soon. Okay, so for the specific one loop effect that we computed a few slides ago, we really know the coefficient, and that gives a very that gives a specific time scale. Okay, if you just compare the coefficient of this correction to the leading behavior, that gives you a time scale. This is, I think, in effective field theory terminology, you would say this is the strong coupling scale of the hydrodynamic effective field. It's not consistent for it to emerge earlier. So the system can't have thermalized earlier. This is a kind of bottoms-up bound on thermalization. So this bound applies in for any, let's say, diffusive system. Let's look at it in the case of CFT, where things are kind of nice and scale nicely. So in a CFT, a lot of these Wilsonian functions become simple Wilsonian coefficients, right? Thanks to scale invariance. So for example, the entropy density is completely fixed to be some dimensionless number times temperature to some power. Same with the diffusion constant. In fact, this entropy density we know very well. This is equilibrium data, so there's excellent. You can do imaginary time simulations, for example, to get this for your favorite CFT for 3D Ising. It's order 1. You can also compute it perturbatively. The diffusion constants, this is a much more non-trivial transport parameter. So this you actually need real-time data to evaluate it. But in principle, we expect diffusion to be given, just by scale invariance, by some order 1 number that is part of the CFT data. It's really dissipative data divided by temperature. So we can plug, what's kind of nice here is that we really know the nonlinearities, right? We know the nonlinear structure just from scale invariance that leads to this temperature dependence. Here I'm talking about energy conservation. There's also momentum, but this temperature dependence leads to nonlinear terms in your effective field theory, which feed back and give power law corrections at intermediate times. And so if you plug in these things in this bound, dropping all the order 1 factors, you get some bound on the time, which obviously by dimensional analysis will look Planckian, but it still has these dimensionless numbers, and the diffusivity in particular. Right, and you could think of it also as a lower bound on diffusivity, which for a QFT is measuring 8/s. Yeah, and lower bounds on 8/s have been kind of searched for some time and conjectured for some time. This is a bound that comes from basically just the consistency of hydrodynamics, but it still involves this equilibration time, right? Which you might want to get rid of. And so you can do one more thing, and this is peppering in with a little bit of UVIR type constraints. You also know that for a CFT, hydrodynamics should satisfy causality, should satisfy microcausality, vanishing of commutators outside of the light cone. And so that gives you a constraint, that gives you an actually interesting constraint on hydrodynamics, because diffusion naively wants to leak outside of the light cone, right? Diffusion at early times looks completely acausal. Now that's not a contradiction, because diffusion always emerges and it takes some time to emerge, but it tells you that diffusion can't emerge too soon. So it actually gives you another constraint on this equilibration time, that it better be, the parametric constraint that tells you it better be larger than when these two curves meet, the diffusive front and the light cone. This gives you another bound on the equilibration time, which interestingly is different. And so since it has to be bigger than roughly d and 1/d, it has to be bigger than 1. And if you keep track of factors of the equation of states, you get some power of the entropy density. Okay, so this is essentially the Planckian-like bound for CFTs and quantum filters. Good. So yeah. So I hope this gave you a little bit of yeah.
Can I have a question about this? So in a large N system, is your bound
very weak?
Very weak. Okay.
It's very weak, sadly. Yeah. So the point is that so it's true in a large N system, this would go to 0, right? But it's very weak. And why is it weak? It's clearly not the right strategy, because I'm focusing on fluctuation corrections to hydrodynamics and hoping that these are the bottleneck to thermalization. Okay, these fluctuation corrections would be 1/n suppressed at large N. They're basically the action for hydrodynamics has a free energy, has a susceptibility or free energy in front of it. That's kind of, and if that goes like N, all these loop effects are 1/n suppressed. And so at large N, the true bottleneck for thermalization is not these fluctuation corrections. It's high derivative corrections. And this, I don't know. It would be really cool to say something. About that. So yeah, so Mark points out to precisely the thing one would want to improve in this equation. So this, for let's say 3D Ising is 1. Okay, so that's fine. For QCD, it's 1-ish. But at large N, it's clearly not really utilizing. It seems very weak, and you might still expect a Planckian bound. Although, so yeah, and I've tried to make this precise, and it's a little bit tricky for reasons I can go into. But yeah, this is certainly one direction that one would want to improve. Other questions on the bound? Okay, good. So in my abstract, I was a little bit optimistic in how much I would say. So I do have some other things, but I think I'll maybe it would be better if we have a discussion and talk about some, take some questions. So maybe I'll just mention a few future directions. So I think a general future direction that would be great to pursue is the interplay, these effective field theories with non-perturbative constraints like bootstrap and other things. One maybe specific question is, this Planckian bound here, I really use the formalism of CFT, light cones, and so on. You expect it to be more general, so it would be nice to understand if that's true. And extending these effective field theories to more exotic observables like entanglement, I think is also a very interesting direction. So maybe I'll stop here and take questions.